Hello, this is Simeon and Lukas. We are students at Hochschule Hannover. One day we encountered a problem. The window in the new flat was only headed to the north side. Unfortunately, the light was very rare in the room. It is a lucky coincidence that we are supposed to do a project at our university. So we thought about creating something that can reflect the sunlight to a certain spot, to brighten the room. The idea of making an heliostat was born. There already are a bunch of videos on YouTube showing DIY heliostat, but they only present that it works and not how it works. Today we'll have a closer look on how this microprocessor-powered mirror works. Basically, there are two ways to know where the sun currently is. You can have 4 photosensitive cells to estimate where the sun is. It's precise enough for solar panels to follow the movement of the sun, but it's not accurate enough to have a low tolerance moving mirror pointing at a window. The other way is to just calculate where the sun should be. For this calculation, it needs GPS and the time, because the sun is predictable and less impulsive. But first, let's take a look at the data sheet.
This is the data sheet from the gear and the motor that we ordered. We spent some time looking for a drive that fits our specification. There were none on eBay or other shopping sites to order right away. So we had to email some companies on Alibaba to get some offers. In the end, we spent €440 for a little bit oversized gearbox with DC motors. And 4 weeks later, we got it. We see the dimensions which were necessary for the hardware to build, the wire define, which were wrong, and some more specification as the rated output speed as low as 21 minutes per revolution, but perfect for us due to the sun is even slower. You can see the massive holding torque of 2200 Newton meter thanks to the worm gear. And the inbuilt sensor is a Hall sensor. It gives high signals twice per revolution. With the 2 different gear ratios, 62 and 575 to 1, we had to do some calculations. We get 198 high signals per degree. This was necessary later for the ESP32 to keep track of the motor movements. To be sure our calculation is right and the ESP32 gets all the high signals, we made a small test. We wrote a program that counts all the high signals. And we drove with the mirror 90 degrees using a level. And it was surprisingly precise. Using the free software TinyCAD, we make this little circuit diagram where we can see all the electric components and the wires connecting them. We see the 24 volts going to 4 relays. We need 2 relays for each motor to change the direction of the motors. We see the 24 volts are also going to a DC-DC step down. It's stepping down the voltage to 5 volt to power up the ESP32. We see the RTC real-time clock is connected to the ESP32. We have the number pad here to drive the motors manually. Yeah, that's pretty much it. We have 4 outputs for each relay. And it looks much more clean here on this diagram than in real life. Luckily, we have a 3D printer at home, so we can print a 3D board to put all our electronic components. So we download Fusion 360 and make a 3D model. It looks pretty easy here, but it took a while to make such a model. And you can see the tiny printer, how it's printing the board.
So, this is what it's all about. The mirror. For our prototype, we got a pretty cheap one from a second hand. For our case, this size fits well. But later, we can mount a bigger mirror for bigger experience. To hold the mirror, we have clamps with rubber as a protection. 2mm ankle steel. They are mounted to these plywood plates and then mounted to the gearbox. This gearbox is for the altitude. It consists of worm gear. The worm is turned by this big black 24-volt DC motor. Then the second gearbox, which is also worm gear, is for the horizontal movement, powered by the same kind of motor. The stand is made out of wood. It's stable enough for our prototype. It's even painted in green color, and furthermore, it's weather resistant. To power up the system, we are now using our DIY camping power supply, which is made in an earlier project. For now, it needs to be powered by a 230-watt supply, but in the future it should be self-sufficient by using small solar panels. Only 3 cables are going inside the terminal box. There's a power supply and 2 cables for the motors. The biggest piece is the 24-volt transformer, which is mounted below the black 3D printed plate. To choose the size of the power supply unit, we looked into the datasheet to see how much amps the motor needs. It's 1.9 amps each. Therefore, we choose a power supply unit with 120 watts, 5 amps, 24 volts. To power up our microcontroller, we have to use a DC-DC step-down converter. It has an output of 5 volts. This is the ESP32, the brain of our machine. The microcontroller is mounted on another development board. You can just screw the wires or use jumper cables to connect the pins. 7 of those jumper cables are currently in use for the number pad. This number pad is moving the axis manually. Number 5 sets the position. The ESP32 has 4 outputs to make relays switch. The relay has 3 pins, 5 volt, ground and a signal for the ESP32. We need 2 relays for each motor to change the directions as we mentioned earlier. You can see in here the relay is working when we press a number at the pad. This is the RTC module. It's the real-time clock. It tells the ESP32 the time and has a battery to make it work even when it's unplugged. It needs the time, the date and the GPS to know the exact position of the sun. Here you can see the insulating screw joints to connect the cable from the motor to the wires inside the terminal box. The current flows all the way from here to there inside this powerful DC motor. To prepare the plate for the mirror, we have to measure the right distances. It is important that we measure the correct dimensions of the motor. Every millimeter is significant for that. Then we are able to drill some holes. With the drilling machine, it is no problem to continue our precise work. The mirror fits right in there. We use clamps to attach it. It is mounted on ankle steel. Moreover, it is attached to some plywood plates. But first, we have to saw them in the right size. No problem at all for our sawing machine. Those insulating screw joints are for the 24-volt power supply unit. We use a screwdriver to attach them carefully. We add a power cable, and that's how it looks like when the wire connections are inside the terminal box. The RTC module needs to be connected with ground, power supply and a signal for the microcontroller. To control the motor, we connect 4 relays in our box. The components find their space at our self-made 3D printed plate.
Here we see the program running on the ESP32. We're including libraries for the real-time clock and the keypad, and what is very necessary is this utility header file. This is to calculate the position of the sun. We found this in a paper online. It's a pretty difficult calculation, and we're just giving it the position and the time and the day since 2000. So let's see our main program, how it works. Here we set the position, which is currently our university in Hanover, but later we're gonna upgrade this with a GPS module. So to initialize the motor, we say it is, when it starts up, it's 90 degrees in the altitude and 180 degrees facing to the south. Here are the pins for the ESP32 to know which pin is the signal from the altitude motor. Then this is the output, 2 outputs for left and right, and the Hall sensor to know how many revolutions. We're saving the altitude turns and the azimuth turns, which is 0 when it's 90 degrees and 180 degrees. And then we say plus when the motor is turning right, and we say minus when the motor is turning left. So we can say where the motor is, in which degree at the moment. Here we can see it gives out the position. If we have our laptop connected to the ESP32, we can see in the monitor the azimuth and the altitude, which was calculating. And here we have the sun position. So we give out the days since the year 2000, and this header file calculates the azimuth and the altitude. And then we check if the sun is even up. We look at the altitude, if it's more than 0 and less than 90. And this is the interesting part. We get the current azimuth and altitude, and then we need to see where the motor should go, the desired azimuth and altitude. So we are calculating the heliostat azimuth minus the sun azimuth divided by 2, because it should, to reflect it to the point, we only need to move half the way of the sun movement, and then plus the sun azimuth. So this is where it should go when the sun is moving. And then we move the mirror to the position. This is for the keypad. The number 2 is turning up. Number 6, for example, azimuth, it's turning right. And the number 5 we don't really need, it's position set. But if we stop the motor, it will always calculating the sun's movement, and we don't really need to set the point. It's always where you stop the mirror, it will move with the sun. Yeah, and then currently we have a delay of 1000, so 1 second, but this is maybe too often. Maybe we only need 2 minutes later, so the motor doesn't need to turn so often. Yeah, this is the whole program.
Now you know the basic construction. It's time now for the heliostat to get to work. The mirror is reflecting the light against the wall and inside the building. Other companies offer way more expensive products. Our Heliostat is a much cheaper, much simpler solution. It not only brings more natural light into the life, it also helps to save a lot of energy. And by the way, there's simply nothing better than always having the sunlight just on the perfect spot.